So the listeners improved the future versions of this course. So this is just a pre-course survey. Voluntary take this course. What can you expect as this part of research? What are the risks and possible discomforts? Minimal risk of discomforts. With online surveys. It's a hell of a way to phrase that question, though, honestly. There's a million other ways they could have put that one.
Welcome to Calculus Applied. I'm Juliana Belding, a math professor at Boston College, and this is Peter Garfield, a math professor at UC Santa Barbara. Peter and I met teaching math at Harvard University. We regularly talk together, and our students often ask, like you may be now, how is calculus really used outside of mathematics?
Well, you can find some applied problems in the back of the textbook chapter. We wanted a more satisfying answer. So we decided to ask people who actually use calculus in their work to help us answer this question.
So we interviewed economists and biomathematicians, environmental scientists and applied mathematicians, physicists and statisticians.
In this course, you'll hear their stories and have a chance to try problems like the ones that they tackle, using tools from single variable calculus.
So what is it about calculus that is so useful? One of my favorite quotes about math is from the 18th century mathematician, Joseph Fourier. He said, "Mathematics compares the most diverse phenomenon and discovers the secret analogies that unite them." Calculus is full of these secret analogies. The idea of change, of accumulation, of approximation are everywhere, from price and demand in economics, to population growth and decline, to Einstein's mass energy equivalence. Calculus gives a qualitative and quantitative way to describe these phenomena through derivatives, integrals, and limits.
As we move through this course, one thing you'll also notice is that we talk a lot about models. We'll be looking at situations in which calculus, and math in general, helps people create and analyze models that capture what's going on and allows us to explain or make predictions. Here's a preview.
We'll talk to biomathematician Wes Kane about understanding sudden changes in the environment through differential equations, which are derivative models. Through these models, we'll look at how populations change with time, or food resources, predators, and competition.
We'll talk to Margot Levine, an applied mathematician who studies medical imaging. She'll share a model for X-rays passing through the body, which involves integration, and explain how X-rays are different than CT scans.
We'll talk to physicist Mboyo Esole and analyze Einstein's famous energy and mass equation using Taylor approximation.
We'll model the interplay of price and demand for subway rides using average and instantaneous rates of change, and talk to economist Kiran Gajwani about some factors at play in this model.
While the models we see in this course will probably be new to you, modeling using calculus may be a familiar idea if you've taken a calculus course.
For example, suppose you throw a ball in the air. We can make a mathematical model of this physical situation. In part, this projectile motion was a motivating example for the very invention of calculus. If we describe the height of the ball in feet after t seconds by the equation h of t equals 5 plus 40t minus 16t squared feet, what is this model telling us? The 5 is the initial height in feet, the height at time t equals 0. The derivative can help us with the meaning of the other terms. The velocity is the derivative of the height. So v equals h prime of t equals 40 minus 32t feet per second. So the velocity at time t equals 0 is 40, the initial velocity. The second derivative gives us the acceleration at time t. This is the derivative of the velocity and the second derivative of the height. It's negative 32 feet per second squared. Notice that the acceleration is constant. In fact, you might recognize it. The acceleration is negative 32 feet per second squared. This is g, the acceleration due to gravity at the Earth's surface. So each of the terms in our model for h of t has a purpose, and calculus can explain the role of each term.
And not only that, but calculus explains why this is the right model. If we assume that the acceleration is the constant of gravity, then by integrating this twice, we get the exact model for the height of the ball.
So that was fast. because we hope this was a familiar example, but we want to reassure you that we'll take our time with new models that we encounter. And one thing we'll be doing with all of our models is looking at their uses and their limitations. For example, we can use this projectile motion model to answer questions like how high the ball will go, or what time the ball will land, and how fast it will be going at that moment.
We can also see that we've made many assumptions in our model. We've assumed the acceleration of the ball is that of Earth, but we've also assumed that the ball is slowed by friction or affected by a gusty wind. Assumptions are part of every model and give us insight into those limitations that you mentioned. We'll see in this course how calculus appears in building and understanding much more complicated models.
The idea of altering a model to better fit a real-life situation is another key idea that will come up often in this course.
Welcome again to Calculus Applied.
Alright, we'll do the intro. So, this is the projectile motion model. Not necessarily sure what that means just yet, but I guess we'll get to that as we go through the topic. So welcome to Calculus Applied. In this course, we will go beyond the calculus textbook, working on the protractions. How am I not saying this word correctly? Practitioners? What? Alright, in social life and other physical sciences, to understand calculus and other mathematical models, how calculus and other mathematical models play a role in their work, and key topics will include applications to derivatives, integrals, and other different components. No, quotations. Mathematical models and key parameters. Okay, so we're going to talk on the standard test makers, how we use functions to analyze the difficulty of the test questions, how economic models, interactions of price and demand using rates of change in historical cases and subway ridership, how an X-ray is different from a CT scan, and what this will do, and what this will do with integrals, and how statisticians, wow, that's a rough word to say, how they use functions to model data like income, distributions, and how integral measures chance. Okay, so the Prey model, biological sciences, biologists use different equation models to predict when populations will experience dramatic changes, such as extinction or outbreaks. That's an interesting one. That's definitely an interesting one to find out. How Einstein's energy equation is a more complicated equation. And we'll explore these situations in hands-on ways, looking at the data and graphs and writing equations, doing calculus computations to make educated guesses and predictions. Okay, so we can move on from here.
This is a course to learn how calculus is applied to other fields. This is not a course to learn calculus. We assume you've had a course in differential and integral calculus or taught yourself these concepts. In particular, you'll need to know about derivatives, integrals, and differential equations.
And one section also involves Taylor approximation for those who've learned that. Now, if you're currently taking a calculus course, you can still take part, but you'll want to wait to do certain sections until you've learned what's needed for that section. And to help you figure this out, we've labeled sections with the calculus that section requires.
We developed this course to help you answer the question, how is calculus applied? We want you to see authentic applications and really delve into them in a hands-on way. The course learning goals reflect this. Through this course, the aim is for you to build appreciation for how calculus can be applied to problems in a variety of other fields and be able to give concrete examples of these applications.
Another aim is that you should be able to apply the ideas and tools of calculus which you've already learned to new and authentic situations outside of mathematics.
You should become more comfortable making sense of mathematical models, including the roles of variables, constants, and parameters. And you should appreciate the assumptions and complications that go into modeling real-world situations with math.
So what do you need to get started? a willingness to actively get into the details. You'll be doing computations, looking at data, sketching and altering graphs, writing equations, making educated guesses and predictions. You'll want to have paper and pencil handy. And though this is an online course, you'll encounter some problems that really require you to step away from the screen and write things down.
One other thing. Because this is an online course, we have a broad audience from all over the world. We encourage you to participate in discussion boards and learn from your fellow participants as well. To start, you'll be asked to introduce yourself this first week.
One more thing you might be wondering, do you have to complete the sections in order? Well, the answer is not always. We've designed the course in a particular order, reflecting the usual structure of derivatives, integrals, differential equations, and series. But it's not always necessary to go in the order provided. So we'll make it clear when a section requires a previous one.
A major part of this course is learning to explore new models and equations with familiar tools from calculus. Each section will have low-stakes quizzes between instructional videos to check your understanding as you learn about the application. There will also be some exploratory quizzes graded on completion only, which allow you to explore new ideas and situations before we discuss them formally.
And then each section will end with a section summary quiz. This is to check your basic understanding of the section, give you more practice, and help you bring the ideas all together. There'll be a final assignment too, and we'll share details of that later in the course. So welcome again to Calculus Applied.
And that's the end of that page. Let's move on to the next. So we got the prerequisites, the links, the refreshers, and the resources. So this course is for anyone who has completed or is currently taking a single variable calculus course, differentials or integrals at high school, AP, IB, or college university. You will need to be familiar with derivatives, integrals, differential exponents, as well as functions involving polynomials, exponents, and logarithms. Alright, even if you're not familiar with it, we'll search all this out. We're gonna get familiar with it by doing this course. So this is a course to learn applications of calculus to other fields, and not a course to learn the basics of calculus, which they kind of did state in the video, so I guess that kind of makes sense. So whether you're a student who just arrived into introductory calculus, or a course teacher, or into an introductory course, or a teacher looking for more authentic examples for your classroom, there's something in here for you to learn. So this is for AB calculus, for BC, calculus 1, so these are other resources to learn more calculus. So we can move on from here. Okay, so this is going to be demos. This is going to be verifying windows, going over what we'll be using for the course. Let's just get to the next video, and so we can get on with our class. And if at any point anybody has any questions, you're more than welcome to ask, and I'm happy to answer as best as I can, figuring this out with you. So let's get started. So we're doing our first quiz to get going and thinking about online math quiz format, dynamic graphing, paper, pencil, yada yada yada. Okay, so what's the ball's height? So as a reminder, the velocity of the ball is t. Oh, t is time, and v is going to be t. Okay, so t is time. Velocity equals time. So here, so what's the ball height? Okay, so t is going to be h. Okay, so we got the 40 here, but this is going to be with the 2 on top. So maybe this would be 16, so this would be 32. Let's say that this will be 8. And the 8t plus the 5. Well, then you can carry over the 5 here. This should be 5. So ooh, I don't know. But this is 32. Well, t can't be 32 over 40. It can't be 40 over 32. I don't think it's any of these above. No, so then maybe it's my first choice with the t is 32 seconds. No, that's not it either. Let's show the answer. So the ball height is ht at its maximum. So this would be 0. 0 is going to be the critical point, okay, because it doesn't have anything of value to it as of yet. So then we have the h1 with the t. Yeah, so it was the 32t, which I did have right, minus the 40. But how is this minus 40? It's a 40t. Okay, so it'd be 40 over the 32. Okay, the 40 is in front of it, so I guess that does make sense. Oh, because they cancel. Oh, okay, because we can cancel the t out. Because since we times this by 2, then this becomes the 32t, and then we can cancel out the t and just get them out of the way. Okay, I guess that makes sense, where this is the 32, this is the 40, but then what about the plus 5? It doesn't say anything about that. Well, we do what we can. So this is the right answer, so let's submit that. Let's move on. Alright, so if the ball hits the ground at t at 2.6 seconds, okay, so let's see, so let's go back up to the top. If it hits the ball at 2.6, this is already 32, is the 40 over the 32, so with the 2.6, so we were talking about the v has to equal t. It's going to be in brackets. No. Let's see what the answer is going to be here. I feel like it has to be the v, though. Oh, I'm clicking more than I should here. Okay, let's say. No, it's not that one either. I gotta be. No. H. So this v is going down. The velocity is v times the t. 2.5. So the h has to be the 2.5. Oh, because the h and the t here. That does make sense. Look at all these. Let's get over to the next video. This is going to be the section courses, the sentence structure, required sections. We can always come back to this at any point. This is going to be the grading, PDF distribution, policies. I'm just trying to get to the class, bro. Just trying to get to the class, bro. Let's put this music back on in the meantime. Okay, so we got the social discussion forum. We don't necessarily have to worry about that. This is the community. We can move past this. This is the teacher forum. Using math notations. This will definitely come in handy later. Let's get past section 1. Perfect. Okay, so now we can talk on the item repository theory, and here's our next video. It's about damn time. Nice. Let me pause this music real quick. Bear with me 1 second.
Chances are you've probably taken a test or survey recently. Assessment is everywhere, whether it's a quiz in an online course like this, a poll that tries to gauge political and social attitudes, or a standardized test like the SAT to measure math and verbal ability. So how do test and survey makers choose questions that best capture what they're looking for? What questions help us distinguish between people with varying opinions or abilities in a certain domain? In this section, we'll talk to Joseph J. Williams, a computational cognitive scientist. He'll tell us about the item response model, one of the most widely used models for questions on standardized tests. You'll use dynamic graphing tools to help understand this model, its variables, and parameters. Then we'll hear more about how these models are created and used in putting together a test. Lastly, Joseph will share about his own work on models for enhancing learning. By the end, we hope you'll not only know more about test questions, but be more comfortable with parameters and how to analyze complicated-looking equations. For this section, you'll need to know the basics of differentiation, limits at infinity, and graphing functions. Let's get started.
I'm originally from Trinidad and Tobago, in the Caribbean. If you were curious, that explains the answer. I'm a scientist on the research team at Harvard's Office of the Vice Provost for Advances in Learning, where we work with on-campus and online courses to investigate learning and teaching. My research creates adaptive systems to enhance and personalize people's education by integrating computer science, psychology, and statistics. Now, you've probably taken many tests in your life. You might wonder, what makes a good test question? This series of videos will help you understand that by discussing some mathematical models that are commonly used by test makers. Let's say we're trying to measure some characteristic of people. A characteristic like height or weight can be easily measured with a ruler or a scale. But what about characteristics we can't measure so directly? For example, math ability on the SAT. We call this a latent trait. Attitudes are another example of a latent trait, like a person's attitude towards a social issue. We often measure a latent trait by asking questions on a test or survey. This raises the issue, what makes a question good or bad at measuring a particular latent trait? For example, answer the following trivia questions, which are designed to measure your knowledge of world geography. Try to think about what makes some questions better than others at measuring what you know. We'll come back to these in the next video.
Alright, let's move on to the next one. So we got an exploratory quiz in world geography. As Joseph said, we're interested in some questions that are better than others at measuring the latent trait of the population of people, unlike height. To explore this issue, we created some sample questions about world geography. Answer these questions. Don't worry about getting these questions right, but make notes on how difficult or easy these questions are. Right? Which is the biggest river and the longest? Isn't it the Nile? Or is it the Mississippi? Is it Mississippi? If anybody knows, let me know. Let's go. It was the Nile. Has experienced more earthquakes. Japan. Why do certain regions experience more earthquakes? Not a matter of chance. Tectonic plates, combination of earth and deserts, no. According to modern civilization, how many oceans are there in the world? Isn't it 6? Or is it 5? No, wait, it's 4. It is 5, okay. How many planets are closer to the sun than the Earth is? Alright, now that's an interesting one. No. Is it 2? It's 2? Wow, I didn't know that. Goddamn. I'm just going to show me the answer. It's not going to give me a breakdown. Which country is the closest to the North Pole? Is it Denmark? It may be Russia. Can't be Canada, because Canada's right next to us. No, it's Russia. No, it's Canada. Wow. I had no idea. Volcanoes only exist on dry land. No, that gotta be false. I'm thinking about Hawaii. I don't know. I want to know the formations of volcanoes. What does cause the formation of volcanoes? Guess we can find out, right? Molten rock called magma rises deep from the earth within the Earth's mantle and reaches the surface through cracks of the crust. Carrying the plate boundaries, the tectonic plates move apart, causing the magma to rise. That's interesting. Good to know. Very good. Good to know. Alright, exploratory quizzes. We can move past this. And videos on parameters of the question. Let's go.
Reflecting on the geography questions may have given you some intuition for which questions are good at measuring knowledge. Whether a student gets a question right depends on features or parameters of the question, as well as the student's ability. I'll use the word ability as shorthand for the student characteristic we're trying to measure. In this case, knowledge of world geography. Test designers typically use the term ability, but I don't mean to imply a fixed ability. After all, the goal of education is to change what people know.
It's actually a great way to look at education.
Several parameters of a question can influence whether a
change
student
what
gets it
people
right.
know.
The first is guessing. A guessing parameter represents the chances of getting a question right, regardless of whether the student has low or high ability. A question with a large guessing parameter can be answered correctly even if someone knows nothing about the topic. For example, a true-false question has a large guessing parameter because there's a 50-50 chance of someone with no knowledge of the topic getting the question right. The second issue is difficulty. If a question is harder, a higher level of ability is needed to answer it correctly. The third issue is discrimination. How much does a question discriminate or distinguish between low and high ability students? A question has a large discrimination parameter. If a correct answer gives the test maker confidence that you have a high ability, while an incorrect answer means you're very likely to have low ability. All three of these parameters come together into what's called the item response curve, or IQ.
It's actually an interesting way to look at knowledge. I mean, of course, it's, you know, what you know and how you apply what you know, but I mean, the ability to retain that information, to learn that information, to consistently consume information. I think that's an interesting way is to look at it as your ability to. I mean, I guess they do say that your ability to solve things, but you know, there's a lot of different abilities that come into education, whether it's learning it, whether it's retaining it, whether it's how you learn the information, not just learning it, and yeah, and a bunch of other things. But yeah, definitely an interesting perspective.
Item response function. Item just means we're talking about one particular question, one item on the test. The item response curve for a question models the probability that someone will answer the question correctly, given their level of ability. So let's think about this function.
Now that item response curve is a different point that I don't normally take into consideration. I don't think a lot of us do take it into consideration, even when it comes down to marketing, the choices that we're given and the choices that we have to make when we're, you know, going out to eat. I can't come up with any other examples right now, but there are a million. You know, but you're ordering something. You know, what clothes to buy when you're, you know, going out. You know, what to get your, you know, your husband, your wife, your boyfriend, your girlfriend, whatever the case, gifts. You know, family members. You know, even what to do for yourself, what to wear. So there's a lot of decisions that come into choices, and decision fatigue is also a very big thing. So within the, you know, curve of the question models, I didn't necessarily think about that portion of it either. You know, the ability to even, wait, hold on, let me go back to that. The item response curve, that's what it was. The items and the decisions that have to be made. And now also going back into the other point, your ability to solve problems. And now going into what you're given, the difficulty. Very interesting ways to, you know, map things together, to say the least.
Yes. The item response curve for a question models the probability that someone will answer the question correctly, given their level of ability. So let's think about this function by drawing some axes and sketching the curve. Along the x-axis, we have the independent variable, which will be ability. We denote this by the Greek letter theta. It's standard for a theta of 0 to represent the average ability of people in this area. So what would a very negative theta mean, or a very positive theta? For world geography, a very positive theta might be a professor of geography, someone who spent a lot of time learning about the subject. A very negative theta might be someone who's never formally studied the topic. For example, a child just learning about the world. The output for this function, the y-axis values, are the probability that someone with ability theta gets the question correct. We call this probability P, or P of theta, since it depends on the ability theta.
Wow. Okay, so we got ability and probability. I'm guessing it's going to go into questions right here. So items referred, independent variables. Okay, so this is the chart he was just talking about for the item response curve and focusing on the probability and the chance. Alright, so we can move on to that. This is probably going to be quizzes and questions. Let's see how many quizzes and questions there are. There's only 3 of them. Alright, so let's see. So consider the particular geography reason where P0, what does P0 equal 25 mean? That the probability of, that would mean they would have about a 25% chance, if that's what we're talking about. The probability to answer the questions correctly is 0. The probability that someone with 0 ability in world geography that answers a question is 25%. The probability that someone with an average ability, I think this is going to be this one. No. It would certainly get the question wrong. No, that's not it either. Let's see what the answer was. Didn't I click that one? No, I clicked the top one. With an average ability. That's interesting. Okay, suppose Avi has the ability level A and Blasi has the ability level B. In world geography, consider a particular geography question with the probability of function being 0, so this has to go back to average. Or at least in that sense, I don't know if it'll change now based on the function of the question. What do each of the following statements mean? If PA equals 1, so the probability Avi is more likely to get the question correct than Blasi. One doesn't necessarily mean 1% though. Oh, wait, no, because this is, here's a 1% chance. Let's see, she's definitely going to get the question right. Oh, he has a 50-50 chance. Oh, he's definitely going to get the question wrong. So Avi is more likely to get the question right. Oh, I got the last one wrong, but I got the other two right. The other three right. Let's go. Is it Blasi's more likely to get the? Oh, because she was greater than her. I thought the greater than was eating it up. Oh, because I know what that would be. I don't know. But I'm happy I got those three right. Let's go. So suppose a young child with no formal education, very low, takes the value of 0, takes a world geography quiz, and the question is true or false that volcanoes only exist on dry land, which describes the value for 0. 0 is undefined because the child has no formal education. I don't know, it still might be 0. I don't know if it said that on the chart. That chart that we were looking at before, let's say. No, yeah, that can't be the case. Oh, I clicked this one. That's disrespectful. It would have been, oh, is it true or false? I should have read the question better. She has a 50-50 chance of getting that right. This is what happens when we, don't pay attention. Okay, let's watch another video.
So let's think more about what the graph of P of theta should look like for a question. We'll assume this function is increasing with theta. Why? We expect someone with higher ability in that topic, higher theta, to be more likely to get a question correct than someone with lower ability in that topic. So it makes sense that p of theta should be increasing. But it's not going to go off to infinity or to negative infinity. It will be bounded. That's because p is a probability. So it can't go higher than 1, a 100% chance of getting the question correct, or lower than 0, a 0% chance. So the graph will be bounded above by 1 and below by 0. We'll have something that looks like this. It will have an asymptote at 1. But on the left side, the probability of getting a question right will not typically approach 0. Think of a multiple choice question. Because of that guessing parameter, even someone with very low ability has a chance of getting the question correct, just by guessing. So on the left, the probability function will have an asymptote at the guessing level. Putting everything together, you end up with a sort of S-curve. So now, let's go back to those geography questions. What does a harder question's item response curve look like? What does an easier question's item response curve look like? Think about the 3 question parameters for guessing level, difficulty, and discrimination. How do each of these impact the item response curves of different questions?
Alright, sweet. Now that that's done. Alright, so we're going to get back to this class another time. It's really mad late for me. I'm a little burned and I want to make sure I intake all this information, and we can all come back to this another time. You can always go back and watch the videos. I'm going to post these all on YouTube too. But yeah, I'm going to probably come on and stream some Forza later. So if anybody pops on, I'll see you then.